So let's look at problem 3.5 from the practice exam. It's a relatively simple problem, but kind of emphasizes a couple key points from the chapter. We're told that if the mass of this cylinder C is 50 kilograms, we want to find the mass of the cylinder A in order to hold the assembly in the position shown, which is basically in equilibrium. So the first question you might ask yourself is, how could I ever relate the force, the gravitational force associated with the mass of cylinder C to the gravitational force associated with the mass of cylinder A? And the key content that you need here that we discussed at the beginning of chapter 3 was the fact that the tension in a cable passing over a pulley is constant throughout. So what I'm going to do here is kind of break away and draw a little free body diagram that's kind of decomposing this system into multiple pieces. And I wish your book went over this first. It actually doesn't cover the concept until about chapter 5. But until you see it, it's kind of hard to understand why, when we eventually do the free body diagram, acting on the O connector here, that we can just assume that the tension in this rope corresponds to the gravitational force acting on this cylinder. So I've did this before in a lecture, so if you've seen it, I don't mean to be repetitive, I'm sorry. So this is the weight of cylinder C. This will be the tension. This will be rather the force that the rope exerts on cylinder C, which because of that property that we spoke of previously, so this is kind of the rope going around the pulley, in order for the cylinder to be in equilibrium, this must also be the weight of cylinder C. By Newton's third law, if the cable pulls cylinder C up by its weight, then the cylinder pulls the cable down by its weight. If we again partition the cable kind of around the point of connection here, we see that in order for this whole system to be in equilibrium, that this rope must be in tension with the weight of the rope kind of pulling it apart on that end. And if you'll notice, what we've done here is allowed us to say that when we actually draw the free body diagram on this O connector, that the weight of cylinder C is eventually transferred by this cable pulley system and serves to pull up on this connector at a 30-degree angle. So the key point being that if I remember that the key kind of challenge in these problems is identifying how you draw a free body diagram that has all of your forces of interest. So you kind of just play with it a little bit. We know that we want to relate the gravitational force associated with cylinder C to the gravitational force associated with cylinder A. If we draw a partition here, we definitely will be able to. So just showing what that looks like. We have, since we assume that this cable is in tension, it will be pulling the connector, and I'll just call this FD, to the left. The weight of cylinder A will be pulling it down, so I'll call this WA. And then kind of up at this 30-degree angle, we have the weight of cylinder C, which is transferred through that cable pulley system at a 30-degree angle. So you notice kind of the same argument that we've always used, even though this connector actually has physical dimensions, and you might assume that those need to be included in your model. We can use particle assumptions because these three forces are concurrent. So what that means is that, I mean, it's, as I mentioned before, when you draw a circular connector like this, it kind of looks like a particle anyways. But what we basically have going on in particle analysis is we have force FD pulling in the negative X direction, force WC pulling up at a 30-degree angle, and the force WA pulling downward. And even though it might look like we need to do an entire equilibrium system analysis here, remember that we only need to find the mass of cylinder A in order to keep this entire thing in equilibrium. So we can just look at the Y components here. So if I decompose the sum of all forces in the Y direction, would require me to decompose the force associated with WC. So that would be WC sine 30. That gives me the Y component pulling in the upward direction, minus WA has to equal 0 for this to be in equilibrium, which means that WA must equal WC sine 30, which means that the mass of cylinder A times the acceleration due to gravity must equal the mass of cylinder C times the acceleration due to gravity times the sine of 30 degrees. The acceleration due to gravity cancels. And what that allows us to do is compute the required mass of cylinder A in order to keep this whole thing in equilibrium. And we were able to determine that by just noting that this cable pulley system serves to provide the only upward vertical force that offsets the weight pulling in the downward direction. So what this says is that the mass A must be mass C times sine of 30 degrees. And we have the mass C as 50 kilograms. And if you don't remember the sine of 30, you can put it into your calculator, but it's just going to be a half. And you can see I made this calculation before I started recording the video. So 50 times the sine of 30 just gives me 25, which shows that we were correct. The sine of 30 is just a half. So as long as mass A is 25 kilograms, this thing will stay in equilibrium. So hopefully that was helpful. Pretty simple problem, but it kind of emphasizes one of the key points of chapter 3 was that when you have a cable pulley system, the tension throughout the cable is constant. And that, as I mentioned in the video, just means that the cable doesn't shred or rip apart.